Let's wait 1 minute.
Luca, you have to start the recording.
Yeah, it's already
Yes,
started.
please start the recording, yes.
Yeah, it's already started.
Very good. Okay, maybe we can start now. Hello, everybody. Today we have a great pleasure to have a talk by Juan Maldacena. He will tell us about BFSS conjecture and three-point amplitudes and source theorems. Please, 1 hour, Juan.
Okay, well, thanks for the invitation. It's a pleasure to be here. I hope you can hear me well. So we'll first, this talk will contain two parts. First, I'll give a review of the BFSS conjecture, and then we'll discuss some aspects of the three-point amplitudes and soft theorems according to this conjecture. So the first part is the review. So this is based on this paper of Banks, Fischler, Shenker, and Susskind, called M-theory as a matrix model, a conjecture, from the 1990s. So the idea is that a certain matrix model can be used to compute M-theory scattering amplitudes. So the matrix model is the following. So it's a matrix quantum mechanics theory. So it's a bunch of quantum mechanical degrees of freedom. By quantum mechanics, I mean 0 plus 1 dimensional theory. It is basically a gauge theory. Now, in quantum mechanics, a gauge theory is very simple. It's a theory with a global UN symmetry, with the restriction that we only consider UN invariant states. So the theory has an SO9 symmetry, bosonic symmetry, and 16 supersymmetries. And it contains 9 matrices, 9 bosonic matrices that transform in the usual vector representation of SO9, and then 16 adjoint fermions. So the Lagrangian looks for each of the matrix elements looks essentially like a non-relativistic free particle, plus some potential interactions. So the potential involves, we have a matrix, you take the commutator of the matrices, take the square, and then take the trace over the matrix indices. The fermions are Majorana fermions, so this is the usual Majorana kinetic term. And then there is some interaction, Yukawa-like interactions between the fermions and the scalars. Now, the idea is that we should roughly, we'll see this in more detail later, but we should roughly think of x's as positions of some particles in 11 dimensions, where we think of the particles in Lycon gauge, and these x's are talking about the transverse position in 9 of the 11 dimensions. The Lagrangian contains some coupling constant, which in Planck units, it's in 11-dimensional Planck units, is related to the radius of some Lycon direction. So that's this R appearing here. Now the conjecture is that, of course, you can consider this, sorry, I should have said that you can consider this matrix model independent of any other of this 11-dimensional interpretation. It's just some matrix with some quantum mechanical theory, some specific quantum mechanical theory. Now the conjecture is that a certain Larsen limit of a scattering problem in the matrix model, so we'll see that we can define a scattering problem in the matrix model, that's supposed to be the same as the scattering amplitude in M-theory. I mean, I remind you that M-theory is a theory in 11 dimensions whose low energy limit is 11-dimensional supergravity. And in principle, we don't have an independent way of defining this theory. Well, we have some other ways of defining it using ADS-CFT, but again, using a certain Larsen limit. But what we're going to discuss is one way to define the theory. Now, this scattering problem involves very low energies, and again, in this Larsen limit. And it's not quite the same as the Toft limit of the matrix model. The Toft limit of the matrix model has a more, let's say, conventional gauge theory or gauge gravity interpretation in terms of certain black holes and curved geometry. it involves a 10-dimensional black hole, but that's not what we are talking about. What we'll be talking about is a very low energy limit of the same matrix model, and that's the limit that is relevant for the BFSS discussion. Now, when some of these, let me see, here, sorry, I was missing this transparency. So the potential, as we said, discussed, has many flat directions. And the matrices can become diagonal. Remember that the potential involved commutator of matrices. So if you take a diagonal matrix, then that would be a flat direction or a zero potential direction for this model. The potential is positive definite, so the minima are at 0, and any diagonal matrix corresponds to a 0 of the potential, so we have a continuous manifold of zeros. Of course, it's a lower dimensional manifold than the whole space of configurations. But along this manifold, the potential vanishes exactly classically. And even if we consider quantum corrections, the potential continues to vanish due to supersymmetric cancellations. That second statement would not be true if we didn't have the fermions, but because we have the fermions, then the zeros of the classical zeros of the potential continue to be zeros in the quantum theory. Okay, so these are some of the directions, flat directions of this potential. And so this is a quantum mechanics in n squared dimensions, or 9 times n squared dimensions. And there are further here, we are saying that there are roughly 9 times n sort of exactly flat directions. Now, when some of these diagonal entries are close to each other, we can get bound states. And to discuss that, let me first discuss the simplest example, which is the, we take all the axes to be close to each other. Then these n by n matrices can be separated into matrices that have 0 trace and the trace of the matrix, or the part proportional to identity. We are calling the part proportional to the identity the U1 factor, and the part involving traceless matrices the SUN part of the model. Turns out these two parts do not interact with each other, and this U1 part can be viewed as a kind of center of mass motion of the whole system. And then this SUN part of the matrix can, well, we think it has a single bound state at threshold. So as we said, the supersymmetry implies that the energy is bounded below by 0. And the statement is that exactly at 0 energy, there is a bound state. So we interpret this bound state. Well, the evidence for this bound state comes basically from an index computation. So you can calculate the supersymmetric index of this model. And it's somewhat subtle because it has these flat directions. But it's been argued that the theory has this bound state. And the idea is to interpret this bound state as a single graviton with momentum n over r along a null direction that's been compactified. So we have some x minus direction. And the idea is that we made this direction compact of size r. And so the momentum along this null direction is quantized. And we have n units of that quantized momentum. And this bound state is supposed to describe a single graviton with that momentum. Now, we discussed this U1, or center of mass of degree of freedom, that describes the motion of this graviton in the transverse dimensions. And that involves just purely the center of mass degree of freedom. There is a factor of n because there were n components of the matrix. This factor of r was in the Lagrangian originally, and this then we can interpret as the Hamiltonian of this matrix model as being P plus of the full 11-dimensional theory. So this relationship can be viewed as the on-shell relationship for a 11-dimensional particle whose P minus momentum is this quantity. So in other words, we have this momentum P, which is a momentum we see directly in the quantum mechanics theory. Has basically, the quantum mechanics looks like the quantum mechanics of a non-relativistic particle. So that's just the momentum along the 9 dimensions. P minus is related to the rank of the matrix, and P plus is the Hamiltonian or energy of the problem. and they fill out the 11-dimensional momentum of the particle. And for these bound states that have zero energy in the SUN part, we get the dispersion relation of a massless particle. And the fermions fill out the supermultiplet, so we get all the different polarizations of the graviton. Now imagine that we have one of these matrices X, and we consider a matrix that has the following structure. So we have the matrix will roughly be the following. So we'll have an identity block of n1 times n1 size here, and it's proportional to some x1. x1 are 9 coordinates. And so we have a diagonal block here. We have further diagonal blocks with size n2 and n3. And then the idea is that these x's are all very far from each other. And so we can think of each block as separately as the same as the problem we discussed before. So there will be an SUN1 bound state. And then this x1 is describing some kind of center of mass motion of those degrees of freedom. And similarly with n2 and n3. So the idea is that this, so in the limit that they are very far from each other, we can neglect these off-diagonal components, set them to 0. And then we have 3 separate problems, similar to the one we discussed before. And we think of this as three gravitons with momenta, null momenta, which are pi and I over r. And then they will have 9-dimensional momenta, which have to do with the momenta associated to the center of mass degree of freedom for each of the blocks. So the idea is that when we consider asymptotic directions, which involve these bound states, we are describing 3 independent gravitons. So now that we have this description of the asymptotic states, we can imagine a scattering process in the quantum mechanics theory. All this discussion is purely in the quantum mechanics theory, even though we're using this language from this interpretation from 11 dimensions, but these are just asymptotic directions. We are talking about asymptotic directions in the space of configurations of this 9-dimensional theory. And we are going to scatter these configurations. This is similar to a problem in non-relativistic quantum mechanics that we have a coordinate, let's say, on a half space, and something comes from infinity, goes near the center, it scatters and goes back to infinity. In this case, these directions at infinity correspond to these multi-bound states. So in this case, let's say we have 2 bound states. They're very far away. They start coming closer together. They become some complicated matrix. And then one possibility that would happen is that there are 2 other bound states that go into the asymptotic directions. Of course, we could also have 3 bound states, 5 bound states, etc. This is just one specific example. So that's a scattering problem in the matrix model. We could consider this problem independently of any 11-dimensional interpretation. Then the idea is that we take a large n limit where n goes to infinity and r goes to infinity, keeping this fixed. So we're keeping the momentum fixed. So what this does is it decompactifies this 11-dimensional null coordinate, and it keeps all the momenta fixed. And so that's a certain large n limit we could imagine taking in the matrix model. And this is a very low energy regime in the matrix model, and it corresponds to very strong Toft coupling. So we can think of some Toft coupling of the matrix model, defining an effective coupling in that quantum mechanics theory. It's a dimensionful quantity. We need to divide by essentially the energy cubed of the process we're considering. And when we consider this combination in the context of this limit, we find that this Toft coupling scales like n to the 4th. So it's not staying fixed, it's becoming very large. So we're going to very low energies where the Toft coupling is very large. In the older papers, this limit is stated in this way. It is completely equivalent to what we discussed about. So the statement and the conjecture is that we take the limit of that scattering problem in the matrix model. That's what we have been discussing so far. And that's supposed to be equal to the scattering amplitude in M theory, where of massless gravitons, massless external gravitons, with a momentum that is related to the momentum of the 9 dimensions and the null direction, N9. Now, I should emphasize that the conjecture is that this is the full amplitude in M theory. So this includes, for example, black hole intermediate states, everything. That's the conjecture. And if we further take a limit where these momenta are very small, then we're supposed to get supergravity. That's but it's not just about the supergravity; it's about the full scattering amplitude. Now, there are various sub-conjectures that one could have that are necessary somehow. The first one is that this limit exists, so that we can take the Larsen limit of this scattering problem in the matrix model, and that limit makes sense, and that these quantities do not go to infinity, for example, or that maybe they oscillate very rapidly as a function of n. I mean, those could be some of the ways in which this limit could fail to exist. Conjecture number 2 is that the result of taking this limit is Lorentz invariant. Here, so the matrix model had some symmetries, but there are the symmetry that the Lorentz symmetry that mixes this 9 momenta with this null momentum is certainly not manifest, and is definitely not a symmetry of the matrix model at finite n. But the idea is that in the Larsen limit, it should become a symmetry. So again, that's another conjecture. Another sub-conjecture is that after you take this limit, the theory continues to be unitary. Now, this limit is, of course, before you take the limit, of course, the scattering amplitude is definitely unitary. One way in which it could fail to be unitary after taking the limit is that some of the probability goes into states that are not part of the limit. So, for example, imagine that that you produce states with, let's say, n equal to 1 or 2, so some fixed number. You produce them with finite probability. So then in the infinite n limit and so on, those from the right-hand side point of view would be gravitons with exactly 0 momentum. So we are not supposed to have some finite probability for those states. So that's one way in which it could fail to be unitary, because some of the probability go into states which are not part of the states we normally consider in the space of states of this 11-dimensional problem. So we are thinking that does not happen. So again, conjecture. And well, number 4 is, of course, that it has all the properties we expect from M theory, that it reproduces gravity at low energies, incorporates black holes, and so on. So this, I sort of emphasize this just to emphasize that these are not obvious properties. Now, what can be checked? So there are some old checks that there are very few things that have been checked. So I'll mention them. So
can I ask
yes.
a question?
Yes, please.
Yeah, when you said incorporating black hole, what exactly you mean?
Yeah, incorporating black holes, what it means is that this amplitude contains intermediate states which are black holes. So for example, if you scatter 2 particles at energies bigger than the 11-dimensional Planck scale, then you produce some object that will emit lots of particles as we expect from Hawking radiation.
And the black hole is in higher dimensions, or you?
Yeah, it's a black hole in 11 dimensions. So the idea is
11.
that it's a Schwarzschild black hole in 11 dimensions, for example.
Okay. Thank you.
Or a Kerr black hole in 11 dimensions.
Okay.
Yes, that's the idea. So if you are, I mean, if you were infinitely powerful and you had a quantum computer that allows you to compute all these scattering amplitudes, you could, in principle, check this. It sounds very difficult.
Can I ask a question which is maybe a little less technical and a little more general?
Yes, please. Yeah.
When you're talking about M theory scattering amplitudes, for instance,
yeah,
you're saying that we have a notion of momentum, which implies that we have a notion of a smooth geometry in 11 dimensions.
Yes.
And
yes.
I mean, my question is just that if you're talking about quantum gravity, then shouldn't we expect that these notions should actually be emergent?
Okay, very good. Yes to the answer of your last question. We expect that they should be emergent. However, what is assumed here is just that we have gravity in asymptotically flat space. So in gravity, the idea is that you can impose asymptotic boundary conditions. So let's say asymptotically flat space or asymptotically ADS space boundary conditions. And what that is assuming is that the long distance fluctuations are basically the metric is frozen at long distances. And indeed, it's a property of gravity that quantum fluctuations become smaller and smaller as you go to longer and longer distances. So we think it's consistent to fix the structure of the geometry at very long distances. Of course, and at those long distances is when you set up the scattering problem. So the idea is that you have you have asymptotic states, which are these graviton states, and you set them up infinitely far away, and then they come in. And when they collide, we are not assuming that they are colliding in let's say very rigid flat space. They are colliding in a dynamical geometry. So the geometry could change. It could produce black holes and so on. And that is, according to this conjecture, already taken into account by this matrix model.
So, I mean, in other words, you are already taking the continuum limit of whatever graininess or quantum geometry there is.
Well, I'm only, so I think the important concept that I'm trying to emphasize is that we can fix the asymptotic structure of quantum gravity. So in quantum gravity, the metric fluctuates and so on at short distances, but at long distances, we can freeze it and have a well-defined sort of platform at infinite distance where we can set up a scattering problem. The same thing happens in ADS. Yeah, so that's, yeah. So this is, yeah, so in some sense, this is a background independent description of the process that is independent of the local background of the geometry, but it depends on the asymptotic boundary conditions, because we think that in quantum gravity, we can really impose asymptotic boundary conditions. Okay. Now, so I was going to discuss some checks that were done in the 90s, and so one is that people considered scattering processes where you don't change the null momentum, so same null momentum for incoming and outgoing states, and furthermore, you assume that the momentum transfer is very small. So in this regime, you can do a small velocity approximation, and you can approximate sort of these forces that you see between these bound states in the quantum mechanics theory in a velocity expansion, the term proportional to, well, first of all, there is no term independent of velocity that is related again for this flatness of the potential that we discussed. The term proportional to the velocity square has, again, no R dependence, and then we get the term that goes like v to the fourth. And it turns out that this term can be computed at weak coupling, and it receives no corrections due to supersymmetry. So then we can go to strong coupling, and the coefficient is the same, and indeed agrees with what we expect from gravity. And that the same is true for the next order. But presumably for the other orders, that's not true anymore. So we don't have an easy way to calculate it. But the point is that for these two terms, there is an easy calculation, and that easy calculation gives a result that agrees with gravity. So that's one check. Now then, this theory also, another set of checks that is related to the fact that it has many nice properties under compactification. So you can imagine not the 11-dimensional M theory, but you can compactify one of the spatial circles. Or one of the spatial directions, you make it into a circle, let's say the 9 direction. And in this case, the idea is that instead of considering a matrix quantum mechanics, you have to consider a 1+1 dimensional field theory. So it's basically the same type of theory, but not in 0+1 dimensions, but in 1+1 dimensions. and on a circle which has a size which is essentially the inverse of the size that we had here. And now for small values of the circle, then this 1 + 1 dimensional field theory becomes very on a circle that is very large, because that's the inverse of the size of the circle. And then in that 1 + 1 dimensional theory, we can go to very low energies, and we can go to the moduli space of that theory, which is a symmetric product. And that can also be viewed as the configuration space of free strings in the Lycon gauge. And in this limit, the corrections to this infrared limit look very much like the interactions of strings in Lycon gauge. So this is a nice limit where you recover the string perturbation theory. And if we take M theory in a very tiny circle, it's supposed to reproduce 10-dimensional weakly coupled string theory, and indeed this is happening in this case. So we see we get the right spectrum. In addition, we get the right spectrum of BPS states for the compactified theories, and we can repeat this all the way down to compactifications up to T5, which correspond to 6 non-compact dimensions. But we cannot go to lower number with this method. So it's not completely clear to me why it fails at when we want to go to less than 6 non-compact directions, but that's what was found. Now I should emphasize that it's pretty hard to compute anything in this theory, so it's a very nice conjecture, but unfortunately it is a limit where it's difficult to compute. However, it is a version of holography for flat space, in the sense that not in the sense that we have a theory at the boundary, but in the sense that we have a procedure for determining the S matrix. So in flat space, the observable of a gravitational theory is the S matrix. So this asymptotic scattering, well, this scattering amplitudes of asymptotic states. And this gives us, in principle, a procedure for determining this S matrix. Now, there are many questions one might have, and so these are some questions, for example. The question is where the limit exists. One could wonder where there is an argument somewhat similar to the Toft argument that says that we should expect the limit to exist, but maybe it doesn't tell us exactly what the answer is. And we would like to argue that objects that are outside this limit are produced only with vanishingly small probabilities, for example, sub-blocks with n = 1. We would like to understand that we should be able to recover gravity at low energies. And people have been talking recently about properties of flat space gravity, or celestial holography, or holography in flat space, and asymptotic symmetries and so on. And those are properties which one would like to, for example, see whether this model has or does not have. I'm not going to answer any of these questions, but these are some questions one can think about. Okay, so this finishes the review, and perhaps it's a good moment to ask for further questions about the general idea of the BFSS model. Okay.
Please
Yes.
ask questions.
Okay, very good. So I'm now then going to describe 2 recent papers that we
There is a
wrote with.
question from Carlo,
Yes.
I think.
Yeah, go ahead.
You are muted, Carlo.
Thank you. Just a very short one. I see the sort of elements, the indications of that, but could you give us a sort of sense why that particular theory should do that? Do we have a very rough intuition why this matrix thing should work in this way, or just because
Yeah,
it has a symmetries?
okay, yeah,
or...
sorry, I didn't give the motivation, but well, a motivation is, well, let me first give a quick motivation, is that in the type 2A limit, so when the circle is, suppose you have a spatial circle that is very small, then the particles that carry momentum along that circle in the 10-dimensional theory become the so-called D0 branes. So So those are the objects that carry the momentum along this tiny circle. So they carry some electric charge, and now the low energy physics of these D0 branes is given by this matrix model. So if you have n D0 branes, it would be given by this matrix model we just discussed. So the idea is that when you take the large n limit, this circle that was very small is being probed by a momentum that is very, very large because n is very large. And so when n is very large, the idea is that you would not notice that the circle has finite size or even a small size. That's roughly the idea. Yeah.
Thanks.
Okay, so the idea is motivated, and I try to explain it without giving the motivation, just so that it's clear what the statement is. Okay, so now we'll discuss these two recent papers, and what we did in one of them was to compute the simplest on-shell amplitude, which is the 3-point amplitude for general complex momenta. And then once you know this 3-point amplitude, then you can derive the so-called soft theorem. And this is interesting because once you have this soft theorem, then it leads to some argument for Lorentz invariance. So let's first discuss the 3-point amplitude. So the 3-point amplitude is something that vanishes when you are in ordinary Minkowski space, but they are non-vanishing if you analytically continue the momenta, or you make one of the momenta imaginary, basically, or equivalently you go to 2,9 signature as opposed to 1,10 signature. And it was recognized that it is an interesting object to study, let's say, more recently. So that's why it wasn't studied in the 90s. Now, one point about these 3-point amplitudes is that they are essentially determined by Lorentz symmetry. So basically, the Poincare symmetry, just the Poincare symmetry, fixes any 3-point amplitude up to a few coefficients. And if you, in addition, have supersymmetry, it fixes it up to an overall single coefficient. And that single coefficient is essentially square root of G Newton. So there's only one, basically, structure. So we know that M theory might be a mysterious theory, but given the symmetries it has, the 3-point amplitude is completely fixed. This is completely fixed to all orders. It's just determined up to an overall constant, and we can think of defining this overall constant as just G Newton. Now, even though this 3-point amplitude is fixed by the symmetries, it is a non-trivial computation in the matrix model, because the matrix model does not have all these symmetries. So if you are at finite n, we do not have the full Lorentz symmetry. So it is not obvious that we will get an answer that will agree with what we expect from 11-dimensional Lorentz symmetry. So suppose we have 3 momenta with non-zero null, but we have 3 momenta where p minus is non-zero or non-zero n for each of them. So in the matrix theory, this process involves 2 bound states with n1 and n2 that are joining to make a single bound state, and we want to compute the amplitude of this process. You could view this also as 1 decaying into 2. This is not really a physical decay because of the momenta, one of the momenta is imaginary. So, but that is the idea. So by not physical, what I mean is that it does not happen in ordinary Lorentzian signature. So the strategy that we use to compute this amplitude is based on the following 3 ideas. The first observation is that the kinematics of the on-shell 3-point amplitude, so the configuration of momenta, preserves 1/4 of the supersymmetry. This is true for, in any supersymmetric theory. Then we argue that we then something we do is we compactify one of these extra spatial dimensions so that we transform the problem into that 1+1 dimensional gauge theory problem. And then this helps us because we can translate the computation of the amplitude to compute in a supersymmetric index. And that by, again, using supersymmetry is something that we can go to weak coupling and then compute the index in a simple way. So an index, yeah. So that's the basic idea. So just said more simply, the idea is that after you notice point 1, then you will use some supersymmetric tricks to compute the amplitude. And that's why it becomes computable, even though it involves this strongly coupled theory. So now we'll explain the kinematics of the 3-point amplitude. So by using the symmetries that the matrix model does have, we can translate the problem to a problem that involves momenta purely in 4 of the dimensions as opposed to 11 dimensions. This can be done just with the symmetries that are manifest in the matrix model. And then we have now a configuration in 4 dimensions. So we have the 2 Lycon directions and then 2 additional directions that we're going to call 8 and 9. And the idea is, so we have a P9 and a P8. The idea is that to pick a P8 which is purely imaginary and a P9 that is real. So with that, in that case, then we can set this PC bar equal to 0. And so we can have 3 momenta, let's say 1 with just purely along the null direction, and the other 2 could have momentum along the C direction and nothing in the C bar direction. So this is a configuration of momenta for the 3-point amplitude. You can easily see that these momenta are all null and that they, of course, obey the momentum conservation condition. I mean, N3 is N1 plus N2. So now, in order to check that supersymmetry is preserved, so the variation of the gravitino is proportional, well, to the, it involves a supersymmetry spinor, which generates the supersymmetries, and a P slash. So it's a bit like a Dirac equation on the for this spinor. And if you have a momentum whose square is 0, then this operator here has a non-trivial kernel, so you will have some solutions of this, and these are the preserved supersymmetries by a single massless particle. But if you have several massless particles, then you will have one condition like this for each of the massless particles. And in this case, they boil down to these 2 conditions, which is that the gamma minus and gamma C on epsilon should be 0, and these 2 conditions are compatible with each other. So there is a solution, there is an epsilon which obeys both of these conditions. And this then preserves 1/4 of the supersymmetries. So each of the conditions preserves 1/2, so the 2 together preserve 1/4. So that's the first point. So we found the configuration of momenta and checked that it preserves supersymmetry. Then the idea is to compactify the 9th dimension, and then we go from the matrix quantum mechanics to a 1+1 dimensional matrix gauge theory. And the momentum along the 9th direction then becomes n units of electric flux along this 1+1 dimensional world volume. So the final configuration that we get is somewhat, well, it's similar to, instead of having D0 branes, so in this brane language, we have D1 branes with n units of fundamental string charge. This is just some language if you're familiar with this. If you're not, it's not necessary. So more precisely what we have is a UN gauge theory with n units of electric flux under the overall U1. So now we can think about the scattering process, and we can go to Euclidean time. So when we go to Euclidean time along the x8 direction, we had some imaginary momentum, but once we make the time Euclidean, it means that the position along x8 becomes real. So the position now along x8 will be real, and we have a configuration where the branes are coming together along the x8 direction and joining to make the single state. And so this can be also viewed as a string junction, which contains two types of strings with various charges. Now, the important point is that here we've drawn the Euclidean time direction, and then there is the additional x9 direction that we haven't written. But all these branes, all these objects are extended along the x9 direction. Okay, and we have a circle along that x9 direction, which has periodic boundary conditions for the fermions. So if we think of x9 as the Euclidean time direction, then what we are doing is we're kind of computing a trace of some evolution in imaginary time, where time is the 9 direction, but with a -1 to the f inserted because we have anti-periodic boundary condition for the fermions. So we're really doing, we really have an index computation along this x9 direction. Now then, there is a technical step which this is just to make this calculation a little easier. It involves making these objects not infinite, but making them end on D3 branes. And we chose D3 branes because, well, we can still preserve some of the supersymmetry. So this breaks additional supersymmetry, but we still preserve some of it so that we can still retain calculational control and do the computation. And by making the problem finite, then when we calculate this index, we have a spectrum of the Hamiltonian, which is completely discrete, and we have ground states separated from the excited states, and the calculation becomes completely well-defined. You can view this as a completely technical trick, or you can think of these D3 branes as some kind of operators that create the gravitons. But we don't need to make that interpretation. That interpretation is not very clear. So it's better to think of it as a technical step just to make the calculation simpler. And the nice feature is that Ashok Sen did a computation of this index of, well, essentially this index of this string junction. It's related to dions in SU3 super Yang-Mills theory. If you think of the D3 branes as giving you some super Yang-Mills theory, then it's related to those dions. Now, the computation we want to do is in a slightly different regime than the one that Sen did, but the idea is that for the same reason that he had, we can calculate the index. So in fact, so the final value of the index is this is what Sen computed, and in order to define this index, it's important also there's another technical issue, which is that you have to soak up some fermion zero modes, because otherwise the index would be 0. So the thing that is non-zero is an index, well, it's some partition function where you insert some angular momentum generators, which contain bilinears in fermions, and then these fermions soak up the fermion zero modes, and then you get a finite answer that is independent of couplings and is equal to this simple combination of the charges. And Sen used this using something called the wall crossing formula that I won't get into details. If you don't know what it is, it's some way of computing this index. So that's this computation of the index. Now, I would say some words about the expected 3-point amplitude. So in order to describe the multiplet, the super multiplet, it's useful to use 4-dimensional notation. I mean, given that the momenta were along 4 of the dimensions, we can use 4-dimensional notation for this problem. So in this 4-dimensional notation, we can use these spinor helicity variables, which are used in amplitude computations, where we write the momentum in terms of two spinors, transforming under SL2 times SL2. So they are usually denoted by lambda, and these are, so they have an SL2 index, and this is SL2 inner product between there are 3 momenta, so there are 3 lambdas, and we have some combination here that is invariant. And then for describing the supersymmetries, we introduce some Grassmann variables, which somehow keep track of how many supercharges we're acting. So we start with, let's say, the positive helicity component of the graviton. That's when you don't have any etas. And then when you start expanding this amplitude in etas, that corresponds to acting with supercharges on the positive helicity graviton, and that fills out the whole multiplet, and it gives us what the amplitude is for all those components. So if you've never seen these formulas, this is just some simple bookkeeping device that allows us to take into account the supersymmetry and the Lorentz symmetry in a very simple way. So that with this single formula, we are describing the 3-point amplitudes involving gravitons and all other particles that exist in this theory. Okay, so or all the various components, but so in 11 dimensions we have the graviton and the 3 form and various components of them along the 4 dimensions, along the other dimensions, and this is describing all of those. So we'll now take this amplitude and we do 3 things. So here I list only 2, so I'm not counting properly. So first we express the amplitude starting from the polarization state created by the D3 brane. So this original amplitude involves the positive helicity graviton. It's better to consider the component of the graviton and 3 form that is created by the D3 branes. So we first do that. And that amounts to doing a Fourier transform of 4 of these Grassmann variables. There are 8 of them. And then we'll set the momenta equal to the values given by, the null momenta and in terms of these discrete charges. So the value of momenta that we had in the theory of interest. So that will give us the expected amplitude. So after a bunch of redefinitions of the eta variables, we get the 2 and 3-point amplitudes. And the 2-point amplitude simply is telling us what the normalization of the states is. And then with that normalization, we can then define the 3-point amplitude. And so the basic point is that, well, this looks like a complicated formula, but let me kind of guide you through it. So let's first start with the 2-point amplitude. So this is basically telling us that, well, the momenta, of course, are conserved, the spatial momenta are conserved, and then these etas keep track of the polarization states. So it tells us that it matches all the various polarization states, and they tell us how many supercharges are acting on so the number of etas here in this formula. So this is something that can be expanded in powers of these etas, and they are telling us how many supercharges are acting on each of the 2 particles that we are having here. For the 3-point amplitude, we have something similar, and we have the particle 3, let's say, and then the particle 1 and 2, and then we can define some center of mass etas for the particle 1 and 2 and some relative ones. And then we can separate this 3-point amplitude into a piece that comes just from the center of mass degrees of freedom that in the matrix model will have to do with the U1 part of the matrix model. And the second line will have to do with the degrees of freedom that are in the SUN of the matrix model. So that's some purely kinematic thing that keeps track of all the supersymmetries. So it's this is just essentially kinematics. And then from the amplitude, we get this somewhat complicated looking function of the ends. And it's not quite equal to the index, and I'll explain why it's not actually equal to the index. But we see at least some combination that was similar to the combination that was appearing in the index, and then some other terms that we're going to argue that they are related to some normalization factors. Okay, so so this is the part that is non-trivial that we would like to reproduce from the matrix model. Now, this computation, in order to explain a little better what this is, so this computation has an open string channel and a closed string channel interpretation. Now, here we have a 2D theory, and when we have a 2D theory with boundary conditions, so the boundary conditions were related to these D3 branes. It's not the worldsheet of a string, so that's why we have quotation marks here. So, but in any 2D theory, we have an interpretation with boundaries. We have an interpretation where if we think of Euclidean time as the circle, then we have a field theory with boundaries, so with two boundaries, and a Hilbert space that is defined, in a space with two boundary conditions. And then we take a trace, more precisely an index in this Hilbert space. That's what we have. This is what we can call the open string interpretation. And then there is another interpretation of the same partition function, which is we view Euclidean time as this horizontal direction. There we have a space which is a circle, and then Euclidean time goes over an interval, and we have some initial state that is determined by the boundary conditions on the left, and some final state that is determined by the boundary conditions on the right, and these are called boundary states. All of this is usually discussed for the string worldsheet, but this type of formalism works for any field theory, even field theories which are not conformal. And here we are discussing it precisely for this 2D theory, which is it's definitely not conformal, and that's the theory where we're doing this computation. Okay, now the idea then here is that these boundary conditions are determined by these D3 branes, and then this computation here really can be broken up into three pieces. So first of all, we have some probability that this boundary state creates creates a graviton, or this bound state for the graviton. So this is this overlap. It's non-zero. Well, it's a non-trivial function. And then similarly for the left side, we have that the left boundary state can create the state of two bound states. And we're going to imagine that this length, this size here is, this x-side separation is very large. So, and then we can split this into the two independent probabilities that the boundary state creates this D3 brane creates one bound state and the other bound state. So we have these other two overlaps. And so we see that the index is not supposed to be equal to the amplitude directly, but is equal to this whole combination of amplitude times these extra overlaps. So that's why the index was not equal directly to the amplitude. So we need to compute these overlaps in order to be able to relate the index to the amplitude. So this whole discussion was to explain that. Now, in order to fix these overlaps, we just look at the two-point function. So when we look at the two-point function, we have a similar interpretation, and we have an index, which again will be essentially 1. And with the other closed string interpretation, we have the square of these overlaps. And in that way, we determine the square of the overlaps, and then once you fix these overlaps, then you can work out explicitly, and we get agreement with the amplitude that we discussed before. So all those other complicated looping coefficients that we have here, they all basically came from those overlaps. Roughly, there is one extra term that is related to this delta function, which has to do with the integral over this interaction point, so that gives an extra factor. But well, you can keep track of all of this, and you get full agreement with the precise functional form of the amplitude expected from 11-dimensional Lorentz symmetry, and even the overall numerical coefficient works out correctly. And now we can take the large n and n limits and recover the amplitudes in the completely uncompactified 11 dimensions. But I should emphasize that we got precise agreement even at finite n and finite little n, which was not necessary for the BFSS conjecture, but well, it's true. So it might be due to the large amount of supersymmetry or the relatively simplicity of the answer. And this is a very simple example of an amplitude that can be computed for generic values of the Ni. Of course, unfortunately, it is a very trivial amplitude in M theory because we expected to have this amplitude anyway. So it's not a new result from the M theory point of view. It follows from the symmetries of 11-dimensional M theory. It's really more a check of the BFSS conjecture. Okay, so are there any questions about this? Okay, so then,
Yeah, can I ask
yes,
some, please, can you return to the formula of third amplitude formula?
yes.
Yeah, and which crossing symmetries do you think correspond into the polarized sector? So when you add some new dimension for polarized sector, which crossing symmetries correspond with this?
I'm not sure I understand what type of symmetries you're asking about, but the structure of the polarizations, which has to do with these Grassmann variables, comes from the supersymmetry algebra. So the anti-commutators of the supersymmetry algebras. Now this
Yeah,
null compactification does not change the supersymmetry algebra at all. We have exactly the same supersymmetry algebra that we had in the non-compact, the theory, the 11-dimensional theory. And so the whole algebra of the Grassmann variables is identical to what we have in the full Lorentz invariant theory. Is that what you were asking, or maybe that's?
so when we say that we can sum correspond symmetries, we some supersymmetry algebra symmetries for crossing between momenta of polarized and unpolarized boson Lorentz invariant sector, which variables, which probability series numerical do you use for this? So it is a probability theory aspect, I think.
Well, I think these are standard amplitudes. It's the same amplitudes we are using in any quantum theory. So it's not yeah, I'm not sure I understand the question. Yeah.
Thanks.
Yeah, sure.
Excuse me, can I ask a question?
Yes.
You consider amplitudes. It's rather difficult to compute them. Let us ask the question about partition function. In 2 dimensions, matrix model is equivalent to the Jakob-Tetey-Bohm gravity. What we can do by analogy in here, I mean partition function for matrix model you consider. Let us compare with 11-dimensional gravity, supergravity partition function.
Yeah.
What do you think?
Yeah. So the matrix model that corresponds to Jakob-Teitelbaum gravity or 2-dimensional gravity is a matrix model of a single matrix. Here we have a more complicated matrix model of many matrices, of 9 matrices and 16 Majorana fermions.
Yeah.
So it's a different matrix model. So there is no connection between the matrix model that describes JT gravity and this matrix model I'm talking about here.
No, I don't mean directly relate with GT gravity. I mean by analogy with 2-dimensional case to consider here independently analogous mechanism. Relate the matrix model by Banks and others with 11-dimension supergravity partition function. Do you know some attempts in this direction?
Well, I think that there is another there is another connection between this matrix model and gravity, which is more in the spirit of standard, let's say, ADS-CFT or gauge gravity duality, which relates this matrix model to a certain 10 or 11-dimensional black hole background. But that's a relation that is relevant at higher energies than the energies we're discussing for these amplitudes. So it's some other application of this matrix model. That's not what I'm talking about here, but yeah, one could also consider it. So if you're interested, I recently wrote a short review on this other interpretation of the matrix model, that basically with the goal of showing that this matrix model might be an interesting target for quantum simulations, because it would give us a background that is described by Einstein's equations.
Mhm. Thank you.
That black hole background. Okay. Now, okay, I think I'm over time, so I'm going to just show
Hey,
one transparency.
no, you can speak 10 minutes more if you like. Yes.
Okay, yes. So yeah, I'll make this somewhat quick. So the idea is that there are these so-called soft factors in gravity amplitude. So if you have a gravity amplitude and you have a graviton with very small momentum, then that amplitude is related to the amplitude well, one less particle times some factors that depend on the soft momentum. And the structure of these soft factors and the actual expression for the soft factors is basically closely related to the 3-point amplitude, because they come from a diagram where there is an almost on-shell particle here. So the soft graviton is interacting with each of the external lines and producing an almost on-shell state here. And that gives, the fact that this is almost on-shell gives rise to this 1/q term here, for example. So given that we got the right 3-point amplitude, you would expect that you will get the right structure of soft factors. So, and that's essentially what we argued. But let me just explain a little bit why we have these soft factors and what the relevance is. So if we are looking at the theory at long distances, the endpoint amplitude basically looks like an endpoint vertex in the effective Lagrangian, right? So we could imagine as an endpoint vertex, and the soft factor is basically saying that we are putting this vertex in a curved background. So we're somehow covariantizing this effective interaction of n particles. And so basically we should be able to consistently couple to a slowly changing gravitational field. That's the soft factors ensure that this can happen, that we can consistently couple to a long distance gravitational field. And furthermore, the consistency of the soft factors implies the Poincare symmetry translations plus Lorentz of the endpoint amplitude. So basically, one can show that these soft factors are obeyed with some assumptions. First, that the amplitudes are suitably analytic. Second is that when the soft momentum and one external line add up to something whose square is 0, so to a non-shell particle, then the amplitude would factorize into the standard 3-point amplitude and the endpoint amplitude. And then if one assumes that in addition that all other singularities, branch cuts and so on, are subleading when we go to small q, so they have higher powers of q when q goes to 0. And while this 3-point amplitude is the standard one, so with these assumptions, then one can show that the soft theorem is obeyed. And then the idea is that these properties are true. Well, we argued that these properties are true in the matrix model. So 1 is essentially an assumption. 2 is related to the scattering properties in the matrix model and the existence in the matrix model of that on-shell intermediate state, which is related to the existence of the bound state. So this 2 is true. 3 is not terribly obvious. It follows from the phase space considerations for multi-particle states, basically for the same reason that it follows from higher loops in gravity. So this is more a hand-waving argument. And well, 4, of course, the 3-point amplitude, we already argued that it was the same as a relativistic one. So maybe I'll skip some of these details. So the idea is that the matrix model obeys those assumptions. And so we can use a contour deformation argument similar to the one that is used by people who study amplitudes, in particular Brito, Cachasso, Feng, and Witten. And we can find an expression for the soft amplitude. So yeah, maybe so that's more or less standard discussion. And then one gets an expression for the soft factors that some explicit expression, which involves the momenta of the n particles, so k runs over the n particles. And this is in the spinor helicity notation. So we use this, again, four-dimensional notation. So that means that our discussion is a bit restricted. It's not as general as we would like it to be, but this is a simple special case. So what's important about this formula is that it involves the soft particle denoted by S and all the n particles, and then it selects one of the n particles as being special. So this expression, which should in principle be completely symmetric, should not select any of the particles, is selecting one of the particles. And here we could have put in any other vector here, and demanding that the answer is independent of this vector imposes momentum conservation of this amplitude. And then there is a similar story with the subleading soft factor, which involves a derivative of the amplitude and selects one special momentum. And if you demand that this expression is independent of this momentum, then this amplitude should be Lorentz invariant. So this of course two facts have been known for a while, that the leading soft factor, the consistency of it implies the energy momentum conservation for the endpoint amplitude, and that the subleading soft factor implies the Lorentz symmetry of the amplitude. And in this context of the matrix model, this was also discussed in this paper. So we see that we get the consistent answer only when the amplitude is Lorentz invariant. So this is interesting because this is not a property we have put in. We have put in some other reasonable properties of the scattering amplitude of the matrix model, and then we are getting that Lorentz invariance. Okay, so now it's important for this argument that we first take the large n limit, and then we take the soft limit. So in particular, there is the null momentum of the n soft that we first take to infinity, but at the rate which is less than the rate at which the n's go to infinity for the other particles. Well, essentially the same rate, but at the ratio which is we're then going to go to 0. So we first take n soft to infinity, keep in the way that we discussed in general for the matrix model. And after we are done with that, then we take the limit that q minus or q soft, q minus soft is going to 0. And it's important to do it in this order because this expression here involves a derivative with respect to lambda, and the interesting Lorentz generator is the one where we take a derivative with respect to p minus. So in conclusion, we've argued that that the soft limits would be correct in the matrix model, and that the consistency of these soft limits implies Lorentz invariance. Okay, thank you. And now, in the future, we would expect perhaps there might be a similar argument to BCFW that might work for showing that the three-level gravity amplitudes are reproduced. So that's not clear, but it's somewhat complicated, but that might be something for the future. Okay, thank you.
Okay, thank you very much for a very interesting talk. You got many new things, and you describe a very interesting perspective for future. Questions, please. I see a question from Shravan. Shravan, please ask your question.
Hi, Juan. Thanks for the nice talk. My question is not directly related to what you presented, but it's a generic question. When you talk about these 11-dimensional black holes, I would like to know how we can learn about astrophysical black holes by studying the 11-dimensional black holes, or how we can relate or learn more from these.
I don't think, well, I don't see anything direct that you could learn in terms of for the big astrophysical black holes. So a reason to study these 11-dimensional black holes, or black holes that we normally study in higher dimensions, is to learn about the information problem. So to learn about conceptual aspects of quantum, to learn about quantum aspects of black holes. And the main goal of those investigations is to understand better quantum gravity.
Okay. Yeah.
And hopefully, so if you're asking me how we plan to connect this to reality and to experiments, the idea would be that to first understand quantum aspects of black holes, and that will teach us some aspects of quantum gravity, perhaps understand better the black hole interior, which looks a bit like a cosmology or a big crunch cosmology. And then from there, maybe somehow time reverse some of the lessons we learn from there and understand some things about big bangs. And perhaps through cosmology, we might have some contact with the experiment.
Okay.
Now, this is a program which, in some sense, so the main message I'm saying is that by studying quantum aspects of black holes, we might learn something that maybe can be applicable in cosmology. And this has already happened. Well, in some sense, it has already happened with Hawking radiation. So Hawking radiation is not something that is relevant for the black holes that we know exist in the universe that are stellar mass or higher. But there is a phenomenon very similar to Hawking radiation that is the creation of particles during inflation, or the thermal aspects of the Sitter space. And that's something that we use for explaining the origin of fluctuations, of primordial fluctuations. So that's an example where some lesson from black holes was somehow transferred to cosmology.
Okay.
Or it's closely connected to something in cosmology.
I have thanks for expressing your view. I have a slightly different question. Basically, here you are talking about compactifications, but when you compute amplitudes, you are computing amplitudes in Minkowski in flat space time. But when you go from higher dimensions to lower dimension with some kind of compactification, isn't it generic to expect curved space-time to appear due to the dynamics of this extra degrees of freedom you generate by compactification? So then you have to deal with understanding quantum fields in curved space-time rather than the flat space-time.
Well, I think, again, the idea is that we, as I said in response to Carlos' question, so we have some compactification and then we go infinitely far away in the non-compact directions, so that we have a kind of frozen geometry and structure far away. And then we can scatter stuff and we can create other, other geometries in the middle, but asymptotically, we never change the asymptotic form of the geometry.
Okay, so you look at asymptotic observables in some
Yeah, we're
sense.
computing the asymptotic observables, but you see, you can scatter things, and in the middle you can change the geometry, and then you create some excitations that then go back again to infinity as stable particles, and you have to read off what you created from the results of this experiment. It's similar to having a collider that makes a tiny little black hole that evaporates very quickly from the output of these collisions, or you would have to figure out what kind of black holes you made.
But even in that case, for example, I mean, the BMS group teaches that even you have to care about the effects of curved space-time, even if you take the asymptotic.
Yes, well, the BMS group is relevant in 4 dimensions. So when and this, as I said in the beginning, this matrix discussion does not work in 4 non-compact dimensions. It works only in high dimensions.
Okay, I see.
So,
thank you.
Okay, let's go to the next question. I see the questions from Dipan Vital. Vital, please ask your question.
Am I audible?
Yes, please.
Is in the matrix model for the quantum system, is there a well-known interpretation of entanglement entropy, and can that be translated as entanglement entropy in the gravity? And could that be helpful in finding that which of the 10 matrices would give us emergent time in the BFSS model, so that the entropy increases with time?
Okay.
Excuse me? Was I audible?
I think
Juan's connection went off.
we lost connection with Juan, yes?
Yeah.
Okay,
We'll-
let's wait for a few minutes, maybe. Let's wait. Still, Juan is not connected. I would like to make some announcement because next week in our institute start a conference devoted to string and quantum field theory. Dima Bykov, are you here? Could you please send the information about this conference to chat for everybody? Are you here?
Yeah, I'll send it now, yes.
Yes, for all people, no, not only for me, yes. Okay, thank you. Okay. Okay, still, I don't see Juan. Oh, thank you. Shravan, okay, maybe you send him email or not?
Okay, I got disconnected somehow.
Yes. Okay, Juan, are you here? Thank you for connecting. I see one more question from Igor Varovich. Okay, Igor, please ask your question.
Okay, thank you for the nice talk. I would like to use this opportunity to ask you about the current situation, your opinion about the information problem from black holes. You wrote many important papers about this. What do you think about current situation?
Well, I mean, in 2019, there were these very interesting papers on the page curve, and I think they explained how to compute the entropy of Hawking radiation. So they gave a more correct way to compute the entropy of Hawking radiation using gravity and obtaining an answer that agrees with information preservation. Now this is, so there are still some open questions. So for example, in particular, there is a method for computing the entropy, but we don't know how to compute the matrix elements. So if you form a black hole and you're asking what the entropy of the outgoing radiation is, you can compute it. You will get, let's say, 0 if the initial entropy was 0. But if you're asking what state comes out, what's the precise state that the radiation comes out when it comes out of the black hole, we cannot give an answer using just purely gravity. We don't know exactly which computation in gravity will tell us this answer.
Do you believe to the complete evaporation of black holes?
Could you repeat that question?
Do you believe to the complete evaporation of black holes?
Yes. Well, okay, so I kind of oversimplified. The information problem can be phrased for a black hole that has not completely evaporated, so that I don't have to answer this question. So you can imagine a black hole that, let's say, forms a very big black hole, and it evaporates up to a size which is fairly small, but still much bigger than the Planck scale. So small compared to the initial size, but much bigger than the Planck scale. So in that situation, that's the situation where you can do calculations in gravity, where we don't have to say anything about what happens after the black hole finally evaporates. And what happens there is that the entropy of the outgoing radiation starts decreasing. So the non-trivial phenomenon that can be understood is that the entropy of the radiation as the black hole forms and starts evaporating rises, and then starts decreasing again at the so-called page time. So that's what can be really argued.
Thank you. Do you think that semi-classical gravity is a good approximation to discuss this problem?
Yes. That was to discuss the problem of the entropy. Yes, it is. That's what's been demonstrated recently.
Okay.
That using semi-classical gravity, one can calculate the entropy.
All right.
Yeah.
Thank you.
Okay, let's go back to questions by Vital. Vital, maybe you repeat your question because I'm not sure, but
Yeah, I didn't hear it,
answer.
so I got disconnected while you were asking.
Okay,
Audible?
shortly repeat your question, yes.
Yeah. Is there a notion of entanglement entropy in the quantum system describing the matrix model, and could that be somehow related to the entanglement entropy in gravity as an area safety or something, some area law or something like that? And would that help us, and would that and could that determine that which of the 10 matrices we can choose as a time direction in order to increase entropy with time?
Well, the matrix model I discussed has 9 matrices, not 10 matrices. There is some other matrix integral called IKKT matrix model, which does have the 10. It's not what I was talking about, but I don't know of a very sharp definition of entanglement entropy in the matrix model, of exactly how you should separate the degrees of freedom, and people have been exploring sort of dividing the range of the matrix and defining some quantities. I think they are somewhat tentative for the time being, but yeah, there is some similar thing you could perhaps define, but it's to be done.
Is there some holographic prescription for the matrix model?
I'm not sure exactly what the question is. So this matrix model gives a somewhat holographic description of the flat space S matrix, in the sense that it's a mechanism for computing the flat space S matrix. Now, there is a separate thing that I did not talk about, which is that if you consider the same matrix models but at higher energies, they have also another more conventional holographic description in terms of 10 or 11 dimensional background, curved background.
Okay, thank you, sir.
Sure, yeah.
Okay, I see a question from Andrea Adazi. Please ask the question, yes.
Yeah, I would like to ask a question from the perspective of the trans-Planckian scattering, because there are several works of Amati, Ciafaloni, and Veneziano, and recently also Colferai, also discussing Bremsstrahlung radiation and soft theorems in trans-Planckian Regge regime. So I would like to ask if you think that from a matrix theory perspective, there would be a regime in which we can connect to this kind of works, because in that regime, you see what you start to see some kind of a coherent state of graviregions, which share some precursor properties of black holes. So I would like to understand if you think that there may be a way to connect the perspective of matrix theory to these studies.
Well, I mean, in matrix theory, in principle, you are describing any regime, including that regime, but this is in principle. And another question is where you can actually do the computation. I don't have any, well, I don't have any idea of how to do that computation, or any. I don't see that the computation could be done in the matrix model. Still, computing almost any amplitude is very difficult.
Okay, thank you.
Yeah, but.
Okay, more questions, please.
Sorry. Can I ask?
Anton, do you want to ask?
Yes, I would like to ask.
Oh, something is wrong. Oof.
Is it possible?
Anton, there is some echo from your
microphone.
From your speaker, yeah.
Could you please just write your question, maybe, in chat?
Is it better now?
Now it's essentially better. Yes, please ask your question.
Yeah, okay, I apologize. There is something wrong with my camera, Juan, but maybe I can, there are a few precisions I wanted to make. This is regarding when you when you are talking about the compactification of this nines direction into effectively describing 1+1 non-relativistic QFT, I'm just wondering how can you consider, and you mentioned in all this conversation with the computation of the superindex, can you implement instead of anti-periodic fermions to implement some quasi-periodicity? Will the superindex computation still hold if, for example, I want to break, if you want a super vacuum in a sense? You understand, usually canonically people have.
Yes. So if you compactify a circle with anti-periodic boundary conditions, then you preserve supersymmetry and will be a stable vacuum.
Yes.
If you compactify the circle and you put anti-periodic boundary condition for the fermions, then you would break supersymmetry.
Right, that's what I'm talking about.
You break supersymmetry, but in addition, this compactification will be unstable. So there is a kind of bubble nucleation that Witten discussed that would produce a bubble of nothing. So it is an unstable, or more precisely, it's a metastable compactification that could decay.
Yeah, I understand, but I'm rather maybe asking a bit even more, because with the periodic or anti-periodic, these are kind of canonical examples where you can compute with an index and your ground state energy of the super vacuum is of course zero. It's not very interesting. But if you do kind of twisting, like what we do in mirror TBA, when, for example, you implement a twist and you start a priori with quasi-periodic conditions. So you are not on either 0 or 1.
Okay. Yeah. I think you could consider such a thing. So you would have to twist, but perhaps by some symmetry of the theory, maybe a rotation.
Yeah. I'm talking about exactly. Very good. Yeah, I'm talking about kind of.
And depending on what you do, it might be. I mean, you might preserve supersymmetry or not. I naively expect that if you don't preserve supersymmetry, it's probably likely to be unstable.
You can preserve part.
Yeah. If you preserve part, then it should be perfectly fine, and well, it would be describing a special type of compactification that you know it will not be translation invariant in the directions in which the rotation is acting, but you can certainly consider such a thing.
Yeah. And maybe a quick point in relation to what you mentioned with the activity of Schoch. I mean, in relation to his, you mentioned this SS3 Yang-Mills dynes, but I think you mentioned that in your case you have fundamental string. So I mean F1 charge, but you were saying in which sense it is related to dynes? You also admit some not just electric but monopoles as well, right? No.
Yes. So you have D3 branes and you have D1 and D3s stretching between them.
Yeah.
The D1 charge is magnetic monopole and fundamental string charge is electric charge of the dion.
So this would be really dion analogs, but in your prescription.
Yes. That configuration is related to dions that have. So in the SU3 theory, there are two U1s, and you can have electric and magnetic charges in there. Those two U1s.
Okay, maybe very last thing. Do you think there are more arguments that could be coming from exactness for this 1+1 non-relativistic QFTs? Like, I mean, do you see any kind of I don't know, like Alasma logic of S-matrix factorizations for the massless sector at least, or something similar? Can it help? Because I have few things in mind that could be also helpful in computation of this overlaps. But of course, I see that you also find other ways how to compute them. But anyway, the short point is: do you see any exact integrability implementation here? Or?
Right. Yeah, I think this gauge theories we were dealing with were not integrable. At least that finite n and so on are not integrable. And but yeah, I don't know. I haven't thought about
but in this
some limit. I guess what you're asking perhaps is whether there is some limit where they become
exactly. More or the like double scaling version. What could be implemented here, or this large n and something. Yeah.
Okay. Well, I mean, there's a general remark, which is that we don't expect that M theory should be integrable because it contains complicated objects such as black holes.
Sure.
But there might be, yeah, there might be some corner which is integrable. I don't know.
Yeah, okay. So my rather question was exactly in terms of some double scale and semi-classics or towards that.
Right.
Yeah,
right.
of course. Yeah. All right. Thank you.
Yeah, sure.
Okay, I see one more question. There is a question from Hong Wu. Hong, please ask your question. Hong Wu.
Okay. So thanks to for your interesting talk. What is the scattering in the slide of open and closing channel? What is scattering? What scattering? You show to scattering N1, N2, N3, but this is what scattering. Yeah.
You were breaking off, so I'm not sure exactly what you're asking, but it was a scattering with complex momenta. So it was an analytic continuation of this 3-point amplitude with complex momenta. That was the amplitude that was considered. It's not something that occurs in ordinary signature, and it's useful for perhaps building other amplitudes. But yeah, so that's what we.
Is this right? In the slide of the scattering string channel and the open string channel.
Yeah, so
excuse me, could you please just write your question?
Yeah, the scattering interpretation was appearing in the closed string channel. The open string channel does not have a scattering interpretation.
Ah, okay.
Okay. Next questions, please. Okay. Maybe I will ask some maybe relevant or not relevant questions. You discuss the relations with amplitude for graviton. Do you expect to get from matrix theory also a higher spin excitations? What do you think? Is it possible to produce some matrix model suitable for to describe high energy spin, high spin excitation?
Yes. So in M theory, we don't expect that those higher spin excitations are stable. So the idea is that we think that the only stable things are just the gravitons. Now, that's again some other conjecture, but if there were stable objects and they can be found in the matrix model, then you could describe their scattering. But the general belief is that there are no other stable particles. Now, you could have unstable states that have spin and so like spinning black holes and so on. But yeah, we don't expect that they should be stable. So they wouldn't be present as asymptotic states. And in this description, we can only talk about the scattering of asymptotic states.
Okay, thank you.
Sure.
Thank you very much. More questions, please? I don't see more questions. If not, let's thank Juan again for his excellent talk. Thank you very much. And we have to ask you, are you not against to put your talk on YouTube?
Yeah,
sure.
go ahead.
because we made your recording. And also, could you please send us your presentation? It will.
Okay, sure. Yeah.
Okay, thank you,
well.
thank you, thank you, thank you very much. Thank you.
Okay, sure. Bye-bye. Best wishes to
Bye-bye.
everyone.
Bye-bye.
Bye-bye. Thank you.
Thank you.
Bye. Thank you, John.
Thank you.
Bye-bye, everyone.
Bye. Thank you.